Hello, ladies and gentlemen. This is Ismail Mutaqi, and I'm presenting our paper, Low-Tech Geometry-Based Node Design for Spatial Structures. After Industrial Revolution in the 19th century, a shift in manufacturing occurred and machines would replace the manual production. The building industry has benefited from this paradigm shift as well. In decades, this caused that mass production shaping most of the buildings and cities. From mass-produced building components such as doors and windows to structural elements like precast beams and columns. However, after a while, the drawbacks of this approach began to appear in this building industry, especially in its humanistic aspect. The user's identity was missing in the mass production of architectural products. This was followed by the next paradigm shift, from mass production to mass customization. With the generous help of computer-aided design and manufacturing, known as CAD/CAM, designers and customers could produce the desired product according to their specific needs and configuration. As an example of the systems that work well with computer-aided systems, the space structures such as space trusses and space frames can be mentioned. These are three-dimensional lightweight structures composed to the discrete linear elements which have been used in the building industry since the start of 20th century. Since the adjustment of these structures with manual methods was time-consuming, even a small change in their parts-spatial relation can result in several changes in the entire structure. However, there are still gaps in the design and fabrication of these structures related to the fabrication methods that make them expensive and unsustainable. The crucial part of these structures, which makes the fabrication difficult, is the design and manufacturing of the nodes. In common 3D structures, such as space trusses and space frames, a large portion of the cost, energy, and time is allocated to the 3D node fabrication. Nodes in space truss systems are fabricated by CNC milling machines, commonly using subtractive fabrication methods. It means that the intended geometry is carved from a solid block of material. This approach is a highly time-consuming, wasteful, and inefficient method, though it is still a dominating way of production. The other problem facing these structures is that the position of the nodes is determined, and the elements must meet the certain points which restrain the overall geometry and network. In this paper, an experiment preliminary results on introducing a novel method to design and fabricate nodes for such structures are discussed. The current methods for production of these structures are contradictory with the nature of the machinery involved. The CNC machinery, in a general sense, is designed to perform programmed tasks which are non-repetitive or differentiable. Yet, we still use them in the exact opposite manner to produce similar parts with the minimum variation. This contradiction is one of the key elements of defining this research. This can be solved using CAD/CAM in a different manner. We are proposing a method to solve the problem via computational geometry. Our method is intuitive and inexpensive in terms of computation and time, and also capable of being integrated in the design process, as the nodes or connecting joints have a critical role in the structural behavior of the system and impose constraints on members' topology and form. In a similar effort in this field, to overcome the challenges of non-standardized elements, scholars used complexity of geometry and network cooperative robotic approach. In this example, more than one articulated 6-axis arms mounted on a 3-axis geometry system are used which is not accessible widely, while in our proposed method, dependency on complex machinery is moderated. In addition to the accessibility, this is obvious that the machinery of 3 or higher axes programming the fabrication is much more difficult. Besides, using more accessible techniques prevents the unnecessary circulation of energy, which results in a more sustainable construction. This shows the importance of moving towards simpler fabrication techniques. With all of this in mind, we are introducing our method which can be fabricated with all kinds of 2 or 2.5 dimensions machines like lasers. In order to start designing the node, a given surface and its generated network for bars are required. The proposed node includes three main elements. First, the main elements shown in red that connect each pair of adjacent linear bars. Second, the shown in blue connectors that link the bars to each node's main elements by an interlocking joint. And finally, the integrators that are shown in yellow. These elements are intended to integrate the entire elements of the spatial joint. To design each node, two parallel aligned planes are located by a specific distance. This distance is dependent on the minimum angle of two adjacent elements. The lower the minimum angle is, the larger the distance gets. The orientation of planes are based on the given surface. They are perpendicular to the given surface and parallel to one of the principal curvatures of the base surface. Using flat, two-dimensional elements not only is in tune with our CNC machine, but also offers a clean and workable intersection area and joints. Then, the intersection of the bars and these planes, combined with a relative offset value, forms a convex geometry for the layout of the parts. Next, the bars are thickened parallel to the normal vector of the base surface. Finally, as the proposed method is designed for 2D manufacturing, a secondary element is placed perpendicular to both the bar and the main element. This element receives the bar and determines the relative positioning and orientation. The shape of the connector elements follows the imposed structural conditions. They are thickened where the bending moment and shear forces are maximized. Here you can see some of the different scenarios the integrators. They consolidate the entire system by retaining the main parts at the proper distance. The number of these elements and their positioning is associated with the forces acting upon the main elements. After designing the node system, we designed and fabricated an architectural scale pavilion to visualize its application. The overall geometry of Twisted Eye Pavilion was designed a double curved surface in order to show the capability of the node system with different complex shapes. Nodes behave desirably regarding the torsion of the base network. The entire structure behaves as a self-supporting structure under the dead loads. Nodes undergo different axial stresses, and therefore the integration of the nodes is examined under tensile and compressive forces and shear forces. We analyze the structure via Karamba 3D plugin, which uses the finite elements method in the Grasshopper environment. You can see the utilization of the structure, which means the amount of stress the entire structure and each bar bear compared to their capacity in the first two figures. The longitudinal shear forces and the axial stresses are depicted in the rest of the diagrams. From the analysis, we realized that the nodes behave semi-rigidly, which offers more stability in the assembling process, and it's compatible with a wider range of networks. Regarding the fabrication, to control the assembling process, elements indicating the structure's footprint have been considered in the design process. By laying these base structures, the rest are woven gradually towards the top of the structure. The assembly of the bars and nodes is done manually, and the construction process took less than 1 day. In conclusion, first we could achieve our main goal of decreasing the amount of material, time, and cost required to design and fabricate the spatial structures nodes using the low-tech machinery. All parts are fabricated with a 2D laser cutter and assembled manually. In addition, as you can see here, these flat members are highly compatible to receive secondary layers of material such as cladding. Next, the proposed system reduces the length, valency, and orientation confinements for the linear elements, allowing creative and new types of structures to emerge, and highly differentiated space frame structures can be manufactured. Then the semi-rigid behavior of the nodes results in the well behavior of the overall geometry. Finally, let's mention that all the challenges discussed in this research are solved by the computational geometry, which is inexpensive in terms of computational time and processes and fully integrated into conventional design tools. Thank you and have a great time all around the world.